first of all, thank you to the organizers for giving me this really amazing opportunity. There are so many amazing talks. I hope that this one doesn't like low the quality of the of the conference. Yeah, sorry also for the title. It's kind of long. So if you want, you can also scan the preprint there. If you don't want, don't mind. I mean, there are more important things to do in life. So I'm Emanuele Costa. I'm from the University of Barcelona. So I'm in between the nuclear group and the quantum many-body group there. First of all, I would like to present and to introduce the people that I work with. So this is a collaboration between the university, so the UAB, the Autonomous University of Barcelona, and the Barcelona Supercomputing Center, and of course the University of Barcelona, because I come from there. So yeah, in order to start this discussion, and so to discuss about this project, I need to explain a little bit the lore of nuclear physics in the era of quantum technologies, because so I would like to put this scheme every time, because so in general many-body theory is like this ensemble of theories, models, and everything. And for example, here we get quantum chemistry and spin systems, because I'm more familiar with these subfields. And I would like to bipartite this set into the physics that we need to study. So the physics that basically is interesting, that you can find on Instagram, or that you can basically use on a date to discuss about, yeah, to convince people that you are cool. And then the enjoyable physics that you like to do. So basically the enjoyable physics is like the physics that releases dopamine when you do it, and that you feel fulfilled, and you feel that you are doing something that's really grateful. And so this triangle is called the triangle of basically joy. Here is nuclear physics, unfortunately. And here there is the nuclear shell model, so it's even far. But however, I mean, I will say that when I started this project, I started with really amazing ideas, and I was with a lot of enthusiasm. Now I'm more practical and more, I will say, disillusioned about all this theory, because it's a really important theory. I would say that if you are familiar with quantum chemistry, it's the corresponding version of the full configuration interaction approach in that framework. So basically you treat nuclei as a bunch of neutrons and protons that live in orbitals. And the cool thing about this model is that, the first cool thing about this model is that basically you can trace out degrees of freedom of nuclei, of neutrons and protons that are in the inner core. So basically subshell, they are filled in the Fermi surface. Also you can avoid valence spaces that are really high energy. And so in this way you can basically describe a large part of the nuclear chart using only particular suborbitals. And this is cool because you reduce a lot of the dimension and you can understand a lot of the nuclear structure in this way. The second cool thing is that this was an idea of Mary Gopper-Mayer, who won the Nobel Prize, so it was the second woman that won the Nobel Prize using this model. So the thing is that this kind of Hamiltonian, it seems like kind of okay, reasonable, but the problem is that the two-body interaction is really complicated. Complicated in the sense that you have a really large tunneling between the single particle states because it's computing using ab initio calculation from quantum chromodynamics and also phenomenological correction. So you can get some microscopical properties of this Hamiltonian, such as rotational invariance, or yes, there is the pairing, there is the quadruple, so the deformation term, but on the microscopical term, it's really difficult to understand. It's really difficult to understand the structure. Moreover, since it's a many-body system, you have basically the dimension that the Hilbert space that scales combinatorially in the following way. So the thing is that since the state of the art of classical computation is exact diagonalization techniques, a couple cluster techniques, and you need a lot of resources to do it, the implementation and so the development of quantum algorithms was a really useful useful development for this kind of field. And so in particular, I'm focused on quantum algorithms for ground state searching, such as VQE and quantum phase estimation. I mean, in particular, with VQE, I don't have a really good relationship. I mean, I'm like, I cannot understand the papers. There are so many cool implementation of VQE, but so far what I understood is that in nuclear, I mean, in this particular framework, VQE shows several issues in terms of convergence and scalability. So the first idea was, okay, cool. Why don't we explore like a quantum adiabatic evolution in this framework? Like we have a quantum system, we have quantum resources, so maybe we just stay quantum and then let's see how it goes. And actually this was Axel's talk. I mean, explain everything really well. I mean, extremely well. I don't judge. I don't want to judge, of course. Sorry. But I mean, it was amazing for me. So this is the thing. So the problem is that since I'm a millennial, so I'm very pessimistic by nature, I immediately started to figure out what are the problems and the drawback of this system. Because, yeah, that's true. This is a time-dependent evolution. Okay, you have your Hamiltonian, you build up this quantum adiabatic time evolution, but the problem is there are no universal quantum annealers where you can map directly these Hamiltonians because, of course, yeah, it's really complicated. So the only way to do it is basically to discretize and digitalize the dynamics. So you start with unitary gates. You act in series these unitary gates, and basically you think, okay, this is kind of okay. I mean, it's standard, it's straightforward. The problem is that when you go with JordanWigner, basically you get lots of CNOT gates. So, and this makes the circuit really unfeasible to use. And the main problem is that, okay, in principle, the scalability of these CNOT gates, so these non-local gates, is polynomial within degrees of freedom of the system. But the problem is that it's still a lot. And the thing that we notice is that the bottleneck is caused by the mapping between fermions and spin and qubit. So we tried to figure out a possible solution on this direction. And the possible solution started from, I mean, we took inspiration considering, for example, condensed matter theory, where you basically deal with Cooper pairs. So basically, you have a fermionic system, and in that particular case, in particular situation, basically the ground state can be represented as a condensate of R-core bosons. The same kind of framework has been implemented in quantum chemistry with the OCI. So the double occupancy configuration interaction, where basically you consider only spin up, spin down electrons in your many-body states, and you can, for example, perform and compute ground state properties of really complicated molecule in that way. So we trying to combine this kind of thing. I mean, we got inspired by this because we cannot invent anything. I mean, I don't have the ability to invent anything from the ground, and so we consider these using the pairing couples as hardcore bosons. Actually, when we were working on that, also we noticed that there is also another amazing group that in Japan. He developed this kind of technique, but focusing only in nuclei where this method is exact, so only considering two valence neutron in the system. So our idea was to generalize this to all the possible nuclear shell model Hamiltonians. So simply, I mean, you can describe basically a fermionic excitation in this way. So you have this horrible fermion, and then you have his minus m counterpart, so the time reversal counterpart. Basically, you force them to stay together. This forcing actually makes sense. So there is a physical insight on this because so in nuclear structure there is the so-called pairing interaction that basically tells you that neutrons and protons with opposite m tend to stay coupled, and this is so a good, I would say, like a good ansatz for and justification for this mapping. At this point, basically, you get a spin excitation, and the spin excitation, of course, because you get an hardcore bosons, so you don't need to take into account the antisymmetry of this system, of these excitations. You don't have to take into account long Pauli strings, for example, in the mapping. Moreover, you get something more, because, for example, if you consider your degrees of freedom, basically what you get is that you can reduce the degrees of freedom by a half, considering this set of quasiparticle pairs. So basically, you have also half degrees of freedom. So everything looks very cool. Basically, you get your quasiparticle Hamiltonian, so you can rewrite it as a spin Hamiltonian with two local interaction. Of course, unfortunately, these coupling, the JAB1 and JAB2, can be computed analytically from the two-body interaction, but they are dense. So basically, you have a all-to-all connection in this sense. And the thing that we notice is that basically, if you try to analyze, so if you try to compute two metrics, so the error in the energy and the error in the and basically the infidelity, so the fidelity of the quasiparticle ground state with respect to the exact ground state, so the full configuration interaction ground state of the nuclear shell model Hamiltonian, what you get is this scheme here, where basically you notice that in the oxygen line, so when the number of protons is 0, and then with different number of neutrons, you get good fidelities and good accuracy in the energy. You also get a mild accuracy in off-diagonal nuclei, so far from the diagonal. What you get in the diagonal, basically, you get really horrible results. And this is because basically the quasiparticle Hamiltonian, of course, I mean, we are reducing a lot, we are simplifying a lot the Hamiltonian, so loses parts of relevant physics that in some cases can completely transform the nuclei. So in the oxygen 22, basically the quasiparticle trick gives you the same structure, but in the neon 20, for example, the wonderful neon 20, you get basically a fake version of it, and you cannot do more in this framework. Okay, so once that basically we consider this, we notice where we can use this quasiparticle approach. We notice that, for example, for the oxygen isotopes that, as I said, I didn't say before, but they are also called semi-magic nuclei. So where the pairing interaction is really strong, is dominant, we get really good approximation. What we were trying to do was to implement the quantum adiabatic evolution using this quasiparticle approach, trying to consider, for example, the number of CNOT, so to see if basically we reduce the complexity. So we basically do the same thing. We consider the driver Hamiltonian. There is the same driver Hamiltonian that Axel introduced in the quasiparticle projection. In this particular case, basically you can encode, we still consider digital quantum computation in this case. So we consider time evolution using unitary gates that basically can be reduced in RXX, RYY terms times other local gates. So basically, for example, in the helium-6, we can directly encode this time evolution using this series of quantum gates. And actually, this is cool also in terms of transpilation, because in the case of the nuclear shell model Hamiltonian, it's really complicated to trotterize and compute and transpile the Hamiltonian. Okay, so the last important result that we got, it's the number of CNOT counts comparing the quantum adiabatic evolution in the quasiparticle case with respect to the nuclear shell model Hamiltonian. So we consider the case where the final state reaches the same level of accuracy with respect to the exact ground state. So basically, we get the same fidelity. That means that, for example, in the oxygen 22, where you get a fidelity of the quasiparticle state at 0.95, you have to take into account that you have to compare this with a time evolution in the nuclear shell model Hamiltonian that gives you the same fidelity. So these are the results. So in overall, basically, we get an improvement of 2-3 order of magnitude in the CNOT counts. The interesting thing is that the structure of these. So if you look at these lines, so basically they are similar in terms of improvements inside each subshell. Each isotope class. That means that basically the structure of the quantum adiabatic evolution, so the levels are similar in these cases, and this is also an interesting result because it's not obvious, of course. And the other thing is that if we look at the scalability of this approach, so in terms of the CNOT, basically we know that if we increase the number of qubits, we still get not an exponential scaling, so it's a power law scaling. That suggests that basically, as we already knew, basically the number of CNOT scales polynomially in these kind of systems. Okay, so the conclusion. Just to recap a little bit, so we explored a direct mapping, a direct spin mapping of the nuclear shell model Hamiltonian, and we noticed that with this class, with some on a subset of nuclei, basically we get basically good approximation. Yeah, they are known as semi-magic nuclei, but also as my favorite nuclei. So the thing is like that also it reduced by 2-3 order of magnitude the computational cost of the time evolution on digital quantum computers. I mean, in this economy, it's very convenient still. And so some perspective and some ideas that I would like to share with you is that now the point is that since I'm basically my heart goes into quantum annealers, I really want to try to bridge the gap between the Hamiltonians that we got to, for example, Ising Hamiltonians in order to map directly this class of Hamiltonian into quantum annealers. And I think that, so I was trying to search in literature that there is some space on doing this. And maybe we can also discuss about this because you are more expert than me on this kind of stuff. Also, in terms of accuracy, because nuclear physicists are really concerned about the energy and all these properties, for sure, because they need to do that. So there are ways to improve the accuracy on the class of nuclei where this method doesn't work properly. So a first idea was to implement, for example, an hybrid fermionic qubit encoding where some degrees of freedom remains fermionic and then you get other degrees of freedom that are quasiparticles to basically improve the accuracy in the ground state energy. Or, for example, by correcting the couplings, so the G terms, using perturbation theory, so for example, considering JordanWigner, and basically introducing again the non-quasiparticle many-body states as a virtual process, and so to correct this coupling and to get the correct ground state energy. So this is everything, and thank you for listening and for the attention.
Thank you for a very entertaining talk. We have lots of time for questions.
Hi, thanks for the nice talk. I was wondering, like in quantum many-body physics, quasiparticles are usually related to the integrability of the system and the first excitations, like the excitations above the ground state. Is there a connection between those quasiparticles directly, which I can see with the quasiparticle models which you are doing here?
Actually, I'm not sure. I don't know about this.
Okay, so can you then explain like exactly why you call them quasiparticles? Like,
that's so that's because the framework was more inspired by Cooper pairs. So the formation of Cooper pairs. So that's the answers of quasiparticles. But for example, in other contexts are called pairing excitations. So in the context of nuclear physics are called pairing excitation. The problem is that, yeah, of course, coming from condensed matter theory, I'm more oriented into use this terminology. But yeah, this is the thing.
Just one other question. So the other thing is, so for some nucleus you saw it was much better than other nucleus. So how much is your method better than mean field approach?
No, okay, it's definitely better than mean field approach. It's definitely better.
Because it's quadratic, right? I saw the interaction was quadratic, so that kind of reminds me of mean field theory. But you take into account some additional higher order terms somehow using quasiparticle.
Because so basically this Hamiltonian, so the nuclear shell model Hamiltonian. So in this particular case, you basically get this two-body interaction. There is is structureless because it comes from phenomenological ab initio calculations. But you can also divide into microscopical terms where you basically add, you have a mean field term. There is a very simple term to encode, also to solve. Then you have a pairing term, and then you have a quadruple term that basically defines the deformation. So in this particular case, we are considering the mean field, the pairing, that in the mean field case is not considered, because the pairing is basically the interaction, is the XXYY term that you get. And there is something more, actually. There is kind of a diagonal part of the quadruple interaction that you get in the NN terms. And basically, so you are doing something kind of slightly more than the pairing approach, but still it's, when, for example, there are high deformed nuclei, of course, like the neon 20 is highly deformed, you get terrible results because, of course, you are missing relevant physics in this framework.
All right. Further questions? All right. Oh, I think you got your hand up slightly faster, so I'll go for you first. I'll get you.
Hi, thank you very much for the entertaining talk. So you do, so you try to solve HNSM and HQ. What are the driver Hamiltonians that you use for both cases?
Yeah, it's okay. I haven't written the driver Hamiltonian, sorry, but it's the same driver Hamiltonian that basically Axel presented. So it's that external field that traps the particles in the initial configuration following the M scheme term. So basically considering the magnitude of the M scheme with the lowest energy subshell. So basically you fill them in quasiparticles. So basically you fill the plus and minus 3/2, plus and minus 1/2 in the 3/2, and then so on and so forth. So this is the driver that we consider here.
Okay, for both the cases.
Sorry?
For both the...
Yeah, for both cases.
Okay,
Yeah.
Thanks.
Thank you.
Hi, so you mentioned that you're using first-order trotterization to decompose your Hamiltonian. Have you looked at higher-order decomposition schemes and how that affects the CNOT count and the runtime?
Yes, we'll look at that, because basically there is a problem. So in some class of nuclei, you can still get in the first order, I mean, for example, so I consider the first order trotterization in the example that we consider. So in the example where I wrote the scheme for the helium 6 with 3 qubits. So in that particular case, basically you don't have so many interaction terms, so basically you can use a first order trotterization term. But for example, in the counting of the CNOT counts, we consider the second order trotterization, Suzuki-Trotter approximation, in both the nuclear shell model Hamiltonian and the quasiparticle. I noticed that, for example, so that the nuclear shell model Hamiltonian, since the number of terms is higher, the number of interaction is higher that you have in the Hamiltonian, it's more sensitive to the approximation, so to trotterization errors. Whereas the quasiparticle Hamiltonian has less terms, so it's less sensitive to this. I didn't mention this because we didn't do a systematic study on this to take into account also that you basically can do second order trotterization and you can stay with that in the quasiparticle case, and you need higher order in the nuclear shell model Hamiltonian where you scale up. we didn't do this analysis, so I couldn't claim so clearly this.
Thank you.
Thank you.
So I might actually ask a question really quick. This might be a dumb question because I'm not a nuclear physicist in any way, but in addition to finding the ground states of these, is the actual dynamics of these systems interesting to people who study nuclear physics? Because you have access to all of that.
Yeah. Actually, that's the thing. Like when I go to conferences of nuclear physics, people are not so interested about the ground state, but they are very curious about the time evolution, because there are so many applications in nuclear physics that are more focused on time evolution. Like, for example, scattering process and other kind of process. So they are really focused on time evolution using quantum technologies in general. So even if, I mean, finding the ground state in general is not a really interesting, I mean, it's an interesting because it's solving the quantum anybody problem, of course.
Sure.
But they are more interested, for example, in transitions. So, for example, in excited states and all these framework. And so, studying the time evolution is an opportunity, and trying to figure out or brainstorm a little bit how to implement these Hamiltonians is a good purpose.
Cool, thanks.
Thank you.
We still have time for another question or two. Matthias?
Sorry, maybe you already answered that implicitly, but just as a clarification, because I didn't catch it. So the Hamiltonian that you're implementing, is that also capable of capturing the dynamics? So could you use the Hamiltonian with your encoding for quantum simulation of the nucleus as well? Or is that...
So this particular Hamiltonian, no.
Okay.
So, and the problem is that also the Nuclear Shell Model Hamiltonian cannot capture relevant dynamics, because since basically you are tracing out degrees of freedom, so you're tracing out orbitals higher energy, when, for example, you want to describe scattering theory or other kind of process, you need the full spectrum, so the full configuration interaction in the sense of the full single particle states that you are considering. So the Nuclear Shell Model Hamiltonian is already an approximation to study nuclear structure or to study electromagnetic, basically transitions that are in the scale of energy of the spectrum that you are considering. So you have to. Yeah, you have to go into more complicated framework. But for example, in that particular framework, you can use ansatz, for example, pairing Hamiltonians, because you don't need this level of information in terms of the structure of the nuclei, so you can schematize better and see in a simpler way the Hamiltonian and the dynamics of the Hamiltonian. And maybe using this quasi-particle approach can also give you important insight in the dynamics. It's like, in general, they use, for example, mean field to describe dynamics of two nuclei that are scattering. You can add more terms to describe this process, adding the pairing approach and using this qubit mapping, for example. I'm just like figure out, like trying to think about it right now. So.
All right, thank you very much.
All right, so that's probably a good place to end the questions. If the next speaker could come down. And yeah, if anyone else has any questions, please feel free to take them offline. And